We're going to review the main types of chemical reactions. The types of chemical reactions are not limited to these. There are redox reactions, acid-base reactions, but those are like specific examples of these categories. So we're going to go over the main categories today. First one is synthesis. It's also called combination. Basically, it's represented by A plus B yields AB. Usually those two reactants are elements, but technically you could have a compound in here as well. But basically you start with more than one reactant and get one product. And again, those reactants can be elements or compounds, but typically we see them as elements. So if we have solid sodium reacting with chlorine gas to create solid sodium chloride, if we write out that word equation, will be Na solid plus Cl2 gas yielding NaCl solid. So it tells you the states of matter, and then Cl2 is a diatomic element, so chlorine gas exists as Cl2, not as Cl. And then the next thing we have to do is consider, is this equation balanced? No, it is not. So there is one sodium on each side, but here on the reactant side we have two chlorine and only one chlorine on the product side. So we can add coefficients to balance this equation, and we can identify it as a synthesis reaction because we have two reactants yielding one type of product, so it is a synthesis or combination reaction. Another common type is the oxidation of metals. So formation of magnesium oxide, which is basically a metal with oxygen as the nonmetal, is the way that you can think about it. It's kind of like when silver rusts or something, basically reacting with air. So here we have magnesium solid reacting with oxygen gas. Again, oxygen gas is oxygen is a diatomic element, so it's always existing as O2. And then if we make sure that we have metal and non-metal here, we got to make sure that the charges cancel out. Since magnesium is +2 and oxygen is -2, that would mean that we have a 1-to-1 ratio, so our chemical formula is going to be MgO. Is this balanced? Not quite, because we have a diatomic element and only one oxygen here, so we can add coefficients to balance that equation, and it is again a synthesis reaction because we have multiple reactants going into a single product. The opposite of synthesis reaction would be a decomposition reaction. So here we start with one compound and we get more than one product. Again, typically it's elements, but you can technically get a compound as a result of a decomposition reaction. One example would be baking soda. Over time it decomposes, and one of the products that you get is a compound, not an element. Most decomp reactions require an input of heat or energy, so some decomposition does occur spontaneously over time, but a lot of times you have to add energy or heat in order to make this happen. So one example is mercury 2 oxide decomposing when heated to produce mercury and oxygen gas. So mercury 2 oxide, we have to figure out what that formula would be. Mercury on the periodic table is Hg. It is a transition element or a transition metal. If it has a +2 charge and oxide always has a -2 charge, that means the chemical formula is just going to be HgO. When we produce mercury and oxygen gas, it tells us that we have oxygen gas, and when we have to decide what's the state of matter of mercury going to be. If you look on ptable.com, mercury is one of those special elements that is not solid or gas at room temperature, it is liquid. So if it's just saying mercury, it's probably mercury in its common state, which would be liquid. So here is our skeletal equation, HgO solid yielding Hg liquid plus O2 gas. And again, oxygen gas in its elemental state as a diatomic element is always going to be O2. We have to make sure that we balance this equation. So on the product side, we have 2 oxygen, but only 1 oxygen on the reactant side. So if we add a 2 on the reactant side, then we have to add a 2 in front of mercury in order to make sure that mercury is also balanced in the end. And we get a balanced chemical equation of 2HgO yielding 2Hg plus O2. So this is again a decomposition reaction. We can see that a compound is being broken down into its elements. The next type of reaction is a single replacement reaction. So in this symbolic equation, you can kind of see that one element is switching places with another. To decide what element will switch with what, you have to consider what would be similar. So for example, if BC is a salt, a metal, and a non-metal, then A would have to replace the thing that is like. So if A is a metal, it's going to replace the metal. If A is a non-metal, it's going to replace the non-metal. You can also consider it in terms of ions. So if we have two anions in the equation, or an element that would form an anion in the equation, it's going to replace the anion in the ionic compound, and a cation would replace the cation. Whether or not a replacement will occur has to do with reactivity of the elements. So there is something called a reactivity series, which is a list of elements, and then the more reactive are usually listed on top, less reactive on the bottom. But basically, the more reactive element can replace the less reactive element. If we have a less reactive element with a more reactive element that is in the compound, then a reaction would not occur. With those problems, a reactivity series would be given on the AP exam for you to decide if a reaction would occur or not. So here we have magnesium that is more reactive than copper. If we have a strip of magnesium placed in an aqueous solution of copper 2 nitrate, it replaces the copper. The products of the reaction are aqueous magnesium nitrate and solid copper metal. So again, since we have magnesium that is more reactive than copper, magnesium is going to replace copper when copper is in this compound. So we can write out this chemical equation. We're starting with magnesium solid and copper 2 nitrate as an aqueous solution, so that means it's mixed with water basically. And then we have a single displacement reaction. Magnesium is going to replace copper to have a magnesium nitrate complex, and then we're going to have copper left over out on its own, which would be solid copper because copper is a solid at room temperature. So here's our skeletal equation. We have to make sure, is this balanced or not? It looks like we have magnesium, 1 on each side, copper, 1 on each side, and nitrate, 2 on each side. So this is already balanced. We do not need to add any coefficients. So here you can tell it is a single replacement reaction because we have something alone in the reactants side replacing something else and leaving that object alone on the product side. Double replacement is very similar to single replacement, but basically you don't end up with an element at the end. You end up with two compounds that basically switch partners. So if you think about it like this couple's dancing, this couple's dancing, if they switch partners, that would be a double replacement. Whereas single replacement, it's like you have 3 people, 2 are dancing, 1's alone, and then the dancers switch and you still end up with someone alone. It's also called double displacement. You will hear replacement or displacement means the exact same thing. I tend to say both. But here we have 2 like elements or ions, so 2 cations or 2 anions that switch places in compounds. So that symbolic equation would be AB plus CD yielding AD and CB. So here A and C switch places, or you could also say that D and B switch places. When we have a precipitation reaction, which is when we have 2 liquids, we add them together, and then we get a solid somehow in the end, that is an example or common example of a double replacement reaction, but is not the only example. And we say that the product, the precipitate, is insoluble. That means it doesn't dissolve in the solution, so you have a solid. So here's one example of a precipitation reaction. We have 2 aqueous solutions, potassium iodide and lead 2 nitrate, that are mixed together. In the end, we get aqueous potassium nitrate and solid lead 2 iodide. So here's our skeletal equation. We have to make sure that it is first balanced. Here we have 1 potassium on each side, but we have 2 iodine on the product side. So I'm going to add a 2 in front of this, which means I have to add a 2 in front of this to balance potassium, and that would also balance my nitrates. So here you can see that we have potassium and lead switching places, and they basically like switch partners. That would be a double displacement or double replacement reaction. The final reaction we'll talk about is combustion reaction. So this is basically occurs whenever you burn anything. With combustion reactions, one of the reactants is always oxygen gas. So that is what is used to burn something. Like when you burn a fire, the fire is consuming oxygen gas. And the products are always heat and light, although they're not always displayed in the chemical equation. And often, like 98% of the time, carbon dioxide and water. And this is going to be true if you have carbon and hydrogen on the reactant side somewhere. Usually they are together as a what we call a carbohydrogen compound, which is carbon and hydrogen. So we have propane gas burning in a grill. We have the chemical formula for propane here. If we are burning it, that means it's a combustion reaction. So even though we don't say that oxygen gas is being added, we know it's added because it's being burned. That is a combustion reaction. O2 is always a reactant. Our two products are going to be, because we have carbon and hydrogen burning in oxygen, we're going to have CO2 and H2O. So here's my skeletal equation. You can tell right away it's not balanced because it's C3H8. We don't have 3 carbons and we don't have 8 hydrogens. So we can balance this equation by adding coefficients, in which we get this equation. So usually for the things I first look for combustion reactions are carbon dioxide and water. Again, because 98% of the time, that's going to be your products for combustion reaction. And the other thing I look for is O2. The thing with just looking for O2 is that formation of the metal oxide that we looked for when we did the combination reactions or synthesis reactions, where we had magnesium and oxygen forming magnesium oxide. So that's not necessarily a combustion reaction. So that's why I always look for these products first. Okay, so that is it for the review of types of chemical reactions. Let me know if you have any questions.